If you ever been asked why did seal fail and the seal temperature was correct and the dwell time was set and you had no answer, this video is for you. Heat sealing looks simple. Two jaws, a film, some heat, some pressure. But what actually holds that package together is a chain of molecular events that happen in a fraction of a second at the polymer interface. And every simple one of those events is governed by the material you choose and the parameters you set. I'm Mo. I have a PhD in polymer science from Polytechnic Montreal, and I work in research and development in the flexible packaging industry. Today, we are going through the complete science of heat sealing, how it works at the molecular level, how to test it, which material seals best, and why, how process parameters control performance, how to model it, and 8 real industrial case studies. This is the most complete guide to heat sealing you will find on YouTube. Let us start. Before we dive in, let me give you a map of what we are covering today. We start with sealing methods, the 4 main techniques used in industry, with focus on heat bar sealing and form-fill seal machines. Then, we go deep into molecular mechanism, 5 steps that occur in fraction of a second when two films are sealed together. After that, test methods, the 2 categories of seal testing, quality tests that find defects and performance tests that measure strengths. Then, sealant materials, polyethylene, polypropylene, EVA, ionomers, acid copolymers, and why their molecular structure determines how they seal. Process parameters, temperature, dwell time, and pressure, and their combined effect on seal strength and hot tack. Modeling and simulation, how mathematical model replace expensive trial and error. And finally, 8 real industrial case studies where we apply all of this to actual sealant selection problems. Let us start with the methods. There are 4 main techniques used to seal plastic packaging, and the choice of method fundamentally affects the machine design, the material requirements, and process parameters. The first one, heat bar sealing. Heat bar sealing is the dominant method in flexible packaging and the focus of most of this video. 2 jaws, at least one of which is heated, pressed together on the film for a defined dwell time. The 3 control parameters are jaw temperature, dwell time, and sealing pressure. The first electrically heated jaw sealer was invented in 1942 for cellophane bags. Today, twin jaw continuous motion VFFS machine can exceed 300 bags per minute. The second one, the VFFS machine, vertical form fill seal, is the workhorse of snack food, coffee, and liquid packaging. Film unwinds from a roll, wraps around a forming tube, gets sealed vertically into a tube. The bottom is sealed, the product is filled in from the top, and the top is sealed and cut. The jaws in the VFFS machine are doing 2 things simultaneously: sealing and pulling the film down. Hot tack strength is critical here because the bottom seal must hold the product weight while still hot. The next one is flow wrapper, a horizontal form fill seal machine. Wraps a film around the product horizontally. A center sealer seals the longitudinal seam beneath the product, and rotating end sealers create the top and bottom seals, common for bars, candies, and bakery products. Ultrasonic sealing uses high-frequency mechanical vibration, 20 to 40 kHz, to generate heat at the interface through intermolecular friction. No external heat source. This is why it is effective for sealing through product contamination and for temperature-sensitive materials like medications, and induction sealing, also called cap sealing, is used for leading rigid container. An electromagnetic field interacts with an aluminum foil layer in the leading structure, generating heat that melts the sealant layer and seals the lid to the container. The cap then removes from the foil, leaving the sealant package underneath. Now the science. What actually happens when 2 films are heat sealed together? There are 5 steps, and each one can limit your final seal strength. The first one, step 1, surface contact. The heated jaw brings the two film surfaces together, but at this point, the interface temperature is still below the melting point. The surfaces have micro-roughness. For a typical polyethylene film, the average surface roughness is around 95 nanometers. This roughness limits the real contact area to a small fraction of the nominal width. Very poor seal strength results if you stop the process here. The second one, step 2, heat transfer. The jaws transfer heat into the film. The interface temperature rises rapidly at first, then more slowly as it approaches jaw temperature. This step depends on jaw temperature, film thickness, thermal conductivity of the polymer, and the crystallinity of the material, because more crystalline polymer take more energy to melt. Step 3, surface melting and rearrangement. When the interface temperature reaches the melting point of the sealant, the surface asperities collapse under the applied pressure. The polymer surface spreads and wets the opposing surface. Maximum contact area is established. This step is also hindered by surface contamination, oil, grease, product residue, which is why hot tack strength is sometimes specified even when the product is not on the seal line. Step 4, molecular interdiffusion. This is the step that actually builds seal strength. Once contact is established and the interface is above the melting point, polymer chain begin to rotate across the interface, diffusing into the opposite film. They form entanglements with chains on the other side. The density and depth of these entanglements determines seal strength. Step 5, cooling and crystallization. After the jaw opens, the sealed area cools. In semi-crystalline polymers, which is most packaging films, the chains begin to crystallize. These crystals act as physical crosslinks. They trap the entanglements formed in the step 4 and dramatically increase the strength of the bond. This is why seal strength measured at room temperature is always higher than hot tack strength measured right after jaw opening. If any of these 5 steps is incomplete, the seal is incomplete. The most important model for understanding molecular interdiffusion in heat sealing is the Reptation model. This model will explain why molecular weight distribution, and chain branching have such large effects on seal performance. The Reptation model says this: a long polymer chain cannot move freely in all directions because it is surrounded by other chains. Those surrounding chains create topological constraints, entanglements, that confine the chain to virtual tube. The chain can only diffuse along the axis of this tube. This snake-like motion is called reptation. There are 3 important time scales. The entanglement time, tau E, is the time for a chain segment to feel the constraints of the tube. The rust relaxation time, tau R, is the time for a chain to relax within its tube. And the disentanglement time, tau D, is the time for the whole chain to leave its original tube completely. In a heat sealing process, the dwell time is almost always much shorter than the disentanglement time of a high molecular weight polymer. This means that we are always in a regime of partial reptation. Chains partially cross the interface and form entanglements, but they have not fully left their tubes. Actually, seal strength is proportional to a square root of dwell time, a direct consequence of reptation. This relationship was confirmed experimentally by Muller. It is one of the most practically useful equations in heat sealing. If you know your seal strength at one dwell time, you can predict it at any other dwell time, and it tells you immediately that doubling dwell time doesn't double seal strength. It increases by only 41%. Now, why does molecular weight matter? Higher molecular weight means longer chains. Longer chains take longer to diffuse. Higher molecular weight increases the seal initiation temperature and slows the buildup of seal strength with dwell time. But once entanglements are formed, higher molecular weight chains have more entanglement per chain, and the final plateau seal strength is higher. And why does metallocene polyethylene consistently outperform conventional LLDPE? In conventional PE, the broad molecular weight distribution means that short, highly branched chains segregate to the surface. This change diffuse quickly, but they are too short to entangle. They provide no seal strength. In metallocene polyethylene, every chain is essentially the same length and branching density, no surface segregation. Every chain that diffuse across the interface forms entanglements. The result is a lower seal initiation temperature and more consistent seal strength at the same condition. Now we need to be able to measure seals, both to detect defects and to quantify strengths. There are two categories of tests, and they are complementary. You need both. The seal quality tests focus on the presence or absence of defects, channels, pinholes, unsealed regions, microbubbles. The result is binary, pass or fail. These tests tell you nothing about how strong the seal is. The seal performance tests measure the strength of the seal in newtons per millimeter or grams per inch. These tests tell you how much force the seal can withstand, but the seal can have a measurable strength and still leak through a channel that is 10 microns wide. Let us start with seal quality tests. Visual inspection is the first and the simplest quality check. Under defined illumination, you examine the seal from 30 to 40 centimeters distance. You can detect channels down to 75 microns with the naked eye. This is always done first. It costs nothing and catches obvious failure immediately. The gross leak or bubble test inflates the package underwater. Any leak produces a stream of air bubbles, visible to eye, detectable down to around 250 microns. This is the standard daily quality check in most flexible packaging operations. The pressure decay test pressurizes the package, then closes the air valve and monitors internal pressure. Any pressure drop indicates a leak. This method can detect leaks down to 10 to the minus 4 standard cubic centimeters per second, very small. The formula is simple. Leak rate equals pressure decay times package volume divided by test duration. The dye penetration test injects a dye solution inside the package and examines the seal under magnifications. Channels appear as colored lines, extremely common in production because it is fast and visual. Technicians can immediately see where the defect is. Airborne ultrasound is the only method that can monitor seal quality in line during production. An ultrasound signal is transmitted through the seal area. Defects absorb or scatter the signal instead of transmitting it. The drop in signal at the detector identifies the defect location, currently limited to line speed below 30 meters per minute. For the seal performance test, the first one, the hot Tack test measures seal strength right after jaw opening. When the polymer is still molten or semi-molten, according to ASTM F1921, the sample is sealed. Then after a defined delay time, the two strips are pulled apart and the peak force is recorded. Hot tack is critical parameters for VFFS applications where the product weight is applied to the hot seal. The seal strength test is done at room temperature. ASTM F88 defines three techniques: unsupported, 90 degrees supported, and 180 degrees supported. The average force in the plateau region of the peel curve is reported seal strength. Note: examine the failure mode as carefully as the number. Adhesive peeling at the interface means the seal is weaker than the film. Cohesive peeling through the sealant layer means the seal is stronger. This is what you want for lock seals. Film breakage means the seal is stronger than the film itself. And finally, the burst test. Pressurize the entire sealed package until failure. The location of failure is the diagnosis. Burst through the film body means the seal are strong enough. Burst at the seal means the seal is the weak link. This test also evaluates the structural integrity of the package as a system. The seal strength versus temperature curve, what we call seal curve, we can see it here, is the signal most important characterization tool for a sealant material. It encodes everything you need to know to set your machine parameters and evaluate a sealant for a specific application. At low jaw temperatures, when we are here on the diagram, the interface temperature never reaches the melting point of the sealant. The chains cannot diffuse. Seal strength is essentially zero. This region is below the seal initiation temperature, TSI. At jaw temperature rises above TSI, the interface temperature crosses the melting point. Chains begin to melt and diffuse. Seal strengths rise steeply with temperature. The rate of increase in this zone reflects how strong crystallinity and molecular architecture limit diffusion near the melting point. At TPI, the plateau initiation temperature, the seal strength reaches a maximum and level off. This plateau represents a state where the entire interface is fully diffused and entangled. Further temperature increase doesn't improve strength. Materials in this plateau region form what is called lock seal, a seal where the material itself will tear before the seal opens. The plateau seal strength must exceed the yield strength of the film for a lock seal behavior. At TPF, the final plateau temperature, seal strength begins to decline. This happens because excessive temperature causes the molten sealant to follow laterally out of the seal zone, what is called squeeze out. The seal becomes thinner, the bound area decreases, and seal strength drops. You can also see visual distortion at the edges of the seal. The seal window is the temperature range between TSI and TPF. This is the practical parameters for industrial sealing. A wide sealing window means your machine temperature can fluctuate to the jaw where seasonal temperature changes or film lot variation without moving outside the acceptable seal strength range. A narrow window means any variation risks going below a spec. Maximizing the sealing windows is the primary goal in sealant design for demanding applications. The hot tack curve follows the same general shape, but peaks at a lower temperature and at a lower force. The reason hot tack is measured in the molten state where chains pull out easily. The main failure mechanism is chain pull-out, which requires less force than the crack propagation and fibril stretching that governs seal strength at room temperature. The difference between hot tack and seal strength reflects the crystallization contribution, the strength added by recrystallization after jaw opening. Now the materials. The choice of sealant material is most fundamental design decision in flexible packaging. Let us go through the major families and understand what their molecular structure means for sealing performance. Polyethylene is the most widely used sealant family. It has no functional groups, just carbon and hydrogen, which gives it chemical resistance, moisture barrier, low cost, and good sealability. But the different types of polyethylene have dramatically different sealing properties, all driven by their molecular architecture. The first one, high density polyethylene, HDPE, has a linear chain structure with very few branches. This allows very high crystallinity, up to 90%, which gives it the highest melting temperature in polyethylene family, 130 to 40 degrees Celsius, and the highest moisture barrier. But the high crystallinity also means a high seal initiation temperature. HDPE is not typically used in sealant layer in flexible packaging. You find it as a liner in multi-wall paper bags. The second one, low-density polyethylene, is made by free radical polymerization in high-pressure tubular reactors. This process creates very long chain branches long enough to entangle themselves. The LCB structure disrupts molecular order and reduces crystallinity and melting temperature to around 100 to 115 degrees. But here is the paradox. LCB also significantly impairs molecular diffusion across the interface. LDPE has poorer hot tag and higher seal initiation temperature than LLDPE despite its lower melting point. LCB is great for melt strength and blown film processing, not for sealing. Linear low-density polyethylene, LLDPE, is a copolymer of ethylene with a short alpha-olefin comonomer, butane, hexane, or octane. These short chain branches are smaller than the critical entanglement molecular weight, so they don't form entanglements themselves. They reduce crystallinity and melting temperature, typically 120 to 125 degrees, while having much less negative effect on diffusion than LCPE. LLDPE is the workhorse sealant in flexible packaging. Metallocene polyethylene, MPE, is produced with metallocene catalyst that gives much higher control over chain microstructure. The result is narrow molecular weight distribution and uniform distribution of short chain branches along every chain. As we discussed with the Reptation model, this eliminates surface segregation and dramatically improves hot tag strength and lowers the seal initiation temperature compared to conventional LLDPE. The price premium is justified by better sealing performance. Polypropylene offers the highest melting temperature in common packaging sealants. Isotactic polypropylene melts at 155 to 160 degrees Celsius. This makes it essential for retort application and microwavable containers where the film must survive sterilization. The penalty is high SIT and reduced clarity. Biaxially oriented polypropylene films use a three-layer structure with polypropylene copolymer skin layers that provide sealability while the polypropylene homopolymer core provides strength. Ionomers, like Sealant, are ethylene methacrylic acid copolymers, where the acid groups are neutralized with metal ions, typically zinc or sodium. The ionic domains act as physical cross-link in the melt, giving ionomers excellent hot tag even at low temperatures, seal-through contamination capability, and fat and grease resistance. These properties make ionomers the preferred sealant for pharmaceutical packaging and any application requiring hermetic sealing under contamination conditions. The trade-off: they are expensive, moisture sensitive, and challenging to process. We touched on this with Reptation model, but let us go through molecular architecture effects systematically, because the literature on this is rich and the implications are very practical. Molecular weight. Increasing molecular weight increases plateau seal strength and hot tack plateau because longer chains form more entanglements per chain once they cross the interface. But increasing molecular weight also raises the seal initiation temperature because higher molecular weight chains need more thermal energy to reach sufficient mobility for diffusion. Researchers showed a linear relationship between maximum hot tack strength and molecular weight for metallocene LLDP, a clean, predictable relationship that doesn't exist for conventional polyethylene because of the surface segregation effect. Molecular weight distribution. Narrow is better. With narrow molecular weight distribution, every chain at the surface has similar mobility, similar diffusion rate, and similar entanglement potential. The sealing onset is sharp and predictable with broad molecular weight distribution. The short chains dominate surface behavior. They diffuse quickly but contribute nothing to the strength, while the long chains are slow to respond. The result is broader, less efficient transition from no seal to full seal. Long chain branches are the enemy of sealing. Even small amounts of LCB, or 0.19 per 10,000 carbon atoms, measurably reduce hot tack strength at LCB densities comparable to conventional LEPE. Hot tack is dramatically reduced. The mechanism: LCB increases the effective entanglement density with neighboring chains in the bulk, making reptation much slower and more constrained. The chain cannot easily thread the tube when it has branches sticking out in all directions. Short chain branches have a much milder negative effect on diffusion because they are below the critical entanglement molecular weight. Their main effect is crystallinity reduction, which lowers melting point and SIT. Higher short chain branches content means a lower melting point, lower initiation temperature, and better low temperature sealing, all positive for packaging. Crystallinity has two competing effects on sealing. During the heating stage, higher crystallinity means more energy needed to melt the interface. A slower approach to the sealing temperature, higher SIT. But after sealing, higher crystallinity means faster, more complete crystallization during cooling, which locks more entanglements and contributes to higher final seal strength. The optimum depends on application. For VFFS, where hot tack is critical, lower crystallinity is preferred. For lock seal applications requiring maximum ambient temperature strength, higher post-seal crystallinity is beneficial. Let us look at the three process parameters that actually control on the machine and how each one affects seal performance. The first one, temperature. Temperature is the most critical of the three. Every aspect of seal performance, SIT, hot tack, plateau, sealing window, is governed by temperature. The reason is fundamental. Temperature controls both the rate of melting and the rate of molecular diffusion. Above the melting point, even a small increase in temperature can dramatically increase the diffusion coefficient and the depth of chain penetration across the interface. The curve we saw earlier, and we have it here, tells the complete temperature story. Below the TSI, no seal. Between TSI and TPI, seal strength builds rapidly. Above TPI, plateau, lock seal behavior. Above TPF, squeeze out and decay. Industrially, you want to operate in the plateau region with a comfortable margin from both TSI and TPF. One important practical point about temperature. We always talk about jaw temperature because that is what the machine controls. But what matters for sealing is the interface temperature, the temperature at the contact surface between the two films. The interface temperature is always lower than the jaw temperature because heat must conduct through the film. The gap between jaw temperature and interface temperature depends on film thickness, thermal conductivity, and dwell time. Dwell time, the second one, is the production trade-off. More dwell time gives higher interface temperature and more diffusion time, better seals. But more dwell time means fewer packages per minute. The relationship between SS and dwell time follows the square root from the reptation model. So you get diminishing returns. Doubling dwell time gives only 41% more seal strength. This means there is always an optimal dwell time beyond which you are sacrificing productivity for no meaningful gain in seal quality. Reduce dwell time by 0.1 second at 100 packages per minute adds 10 plus million packages per year in capacity. The third one, sealing pressure, is needed to overcome the surface roughness and establish contact between the films. Without sufficient pressure, the surface never achieves the intimate contact needed for interdiffusion. But pressure is the least powerful of the three parameters. Researchers showed that the minimum pressure of about 0.2 megapascals is needed below 125 degrees Celsius. But above that temperature, even this limit disappears. Excessive pressure causes squeeze out. Molten sealant follows laterally out of the seal zone, which thins the seal and reduce bound area. Calcability is a special pressure-related property. The ability of molten sealant to follow into gaps, wrinkles, and contamination at the seal interface. This is critical for packaging of powdery or granule products like coffee or cheese, where product particles inevitably end up in the seal zone. High calcability sealants can encapsulate and seal around contamination. The viscosity at shear rate of 1 to 10 per second is the most relevant parameters for predicting calcability. One of the most valuable advances in heat sealing research in recent years is the development of mathematical models that can predict seal performance without running every combination of material and process conditions experimentally. I don't want to go deep into the modeling and simulation of heat sealing, but a brief introduction to this subject for the modeling and simulation of heat sealing. A comprehensive heat sealing model needs to cover four components: heat transfer from jaw to interface, molecular interdiffusion, a squeeze out flow, and crystallization after jaw opening. No single published model covers all four simultaneously, but each component has been modeled separately, and the results are very useful. The heat transfer model, the first one, uses Fourier law of conduction and a thermal contact resistance model at the jaw film interface. The Cooper-Mickey-Ivanovich model accounts for the fact that the contact between the jaw and the film is not perfect. It depends on surface roughness, hardness, and contact pressure. The model is typically solved using finite element model. COMSOL is commonly used in the literature. Key inputs: jaw temperature, film thickness, thermal conductivity as a function of crystallinity, a specific heat, and contact resistance. What we have an output: interface temperature as a function of dwell time. This output directly fits into the diffusion and crystallization model. The squeeze-out flow model treats the molten sealant as a non-Newtonian fluid and calculates how much material flow laterally out of the seal zone under jaw temperature. For most sealants, the power law model fits well. Viscosity equals K times shear rate to the power of n. The results tell you the squeeze-out fractions what percentages of the original sealant thickness flows out, and whether you are at risk of seal thinning or distortion at a given temperature and pressure combination. The seal strength prediction model uses Reptation scaling law. It is proportional to a squeeze root of dwell time, combined with calculated interface temperature and the material specific diffusion coefficient. This allows predicting the seal strength curve for a new material without running the full experimental matrix. Validation experiments are still needed, but the number of experiments required drops dramatically. For spouted pouches and complex geometries, the modeling insights about calcability is particularly valuable. Researchers showed that while 50-micron sealants show essentially no squeeze-out flow, about 1 to 2%, increasing sealant thickness to 100 micron or more can improve SOF to 25% or more. This quantitative result translates directly into the design recommendation. For demanding calcability application, use a sealant of at least 100 microns. Okay, here we have multi-component sealant fill, blend, and nanocomposite. No single component polymer can satisfy all sealing requirements simultaneously. Blending two or more polymers or adding nanoparticles always engineering sealant performance beyond the limits of any individual material. The most common blend in flexible packaging is LLDP with 10 to 20% LDP. LLDP provides sealing performance, low SIT, good hot tack, high seal strength. LDP, on the other hand, provides the melt strength and flow stability needed for blown film processing. The trade-off: LDP delays seal initiation slightly because its line chain branches slow diffusion, but the processing benefit is worth it, and the effect can be compensated with slightly higher jaw temperature. Metallocene polyethylene blended with conventional LLDP gives a performance gradient. More metallocene polyethylene, lower SIT, better hot tack, more consistent sealing, but higher cost. The optimal blend ratio depends on the required sealing performance and the cost target. This is one of the most active areas of sealant formulation in industry. Peelable seals are a fascinating application of polymer blend thermodynamics. Polybutene 1 blended with polyethylene or polypropylene creates a peelable seal through cohesive failure in the polybutylene 1 phase rather than adhesive failure at the interface. The peel force can be tuned by the PB1 content and morphology. An important complication: PB1 undergoes a slow crystal form transition from Form 2 to Form 1 after processing. This changes the seal behavior over several days after manufacturing. The sealant ages qualifying peelable seal require aging studies, not just immediate testing. EVA. EVA blending with polyethylene reduces seal initiation temperature. The vinyl acetate group in disrupt polyethylene crystallinity. This was the original approach for low temperature sealing before metallocene polyethylene and elastomers become available. EVA is still used for specialty application, particularly packaging of chocolate and cheese, where the package must seal at temperature that don't damage the product. Nanocalate reinforced polyethylene blend are the interesting research area. When nanocalate particles are localized at the interface between two PE faces in the immiscible blend, they create a defined weak plane at the seal interface. This generates a peelable seal with a very wide peelable temperature window. Researcher demonstrates that controlling nanoparticle localization gives you precise control over peel behavior. Sometimes that is much harder to achieve by adjusting blend composition alone. Sustainable packaging is one of the most important challenges facing the flexible packaging industry. Bioplastic sealants, materials that are bio-based, biodegradable, or both, are increasingly being specified by brand owners and regulated by governments. Let us look at the sealing reality of the main bioplastic options. The landscape of bioplastic is more complex than it first appears. Bio-based doesn't mean biodegradable, and biodegradable doesn't mean bio-based. Biopolyethylene from Braskem, made from sugarcane ethanol, is chemically identical to fossil polyethylene and has identical sealing properties. It is not biodegradable. Bio-PET has 30% bio-based content from sugarcane-derived ethylene glycol, but the terphthalate acid is still petroleum-based, and it is not biodegradable. PLA, polylactic acid, is the bioplastic with most packaging traction. It is bio-based from corn, compostable in industrial conditions, has excellent clarity and stiffness, and can be printed on. Its seal initiation temperature for amorphous PLA is around 80 degrees Celsius, actually lower than the conventional polyethylene, which sounds attractive. But PLA has poor toughness and low maintenance, making blown film production challenging, and industrial composting in infrastructure is still limited. PLA doesn't degrade in home compost or in recycling stream. PBAT, sold as EcoFlex by BASF, is petroleum-based but fully biodegradable and compostable. It is too soft and too stiffness to use alone. Blended with PLA, it gives the PLA-PBAT combinations that BASF commercialized as EcoView. Researchers showed that adding PBAT to PLA progressively reduces the seal initiation temperature and improves the hot tag plateau. The more PBAT, the lower the initiation temperature. This makes PLA PBAT blends the most practical, fully compostable sealant system currently available. PCL has a very low melting point of 65 to 80 degrees and is biodegradable. This low melting point makes it attractive as a low temperature sealing layer, but it is low thermal resistance limits standalone use. Researchers studied PLA PCL blends and found that PCL progressively reduces the hot tag initiation temperature of PLA and increases plateau hot tag strength. As PCL content increases from 0 to 100%, initiation temperature drops from around 90 to 50 degrees Celsius. PHB and PHBV. They are produced by microbial fermentation. Both of them are bio-based and biodegradable. PHB has a high melting point around 180 degrees, making it interesting for retort application, but it is very narrow processing windows and brittleness make it extremely difficult to produce flexible films. PHBV has a lower melting point around 145 degrees and better processability, but it's still challenging. These materials are still primary in research and niche application. The bottom line on bioplastic, they can seal, but every option involves some trade-off: cost, processability, narrow sealing window, limit compostability infrastructure, or performance limitation and temperature extremes. Blend strategies, particularly PLA with PBAT and PLA with PCL, are currently the most practical paths to sealable, compostable packaging. Now let us apply everything we have discussed to real sealant design problems. Case 1. Cereal packaging. 700 grams in a pillow pouch on a VFFS. The seal is exposed to product weight while still hot. Hot tag is the governing parameter, using a force balance at the seal. Force equal 0.072 times mass times G divided by package width. The required hot tack is approximately 2 newtons per 25 millimeters. The insights: selecting the highest strength option would be wrong because serial films contain a lot of HDPE for moisture barrier and have low tear resistance in the machine direction. If the seal is stronger than the film, customers cannot open the package. Case 2. Liquid milk, 1.5 liters. Hot tack required 7.35 Newton per 25 millimeter. For liquids, the internal pressure during distribution also stresses the seal. A peelable seal adds no benefit to milk. It only risks spillage. Lock seal with brake failure mode is selected. Case 3. Heavy-duty shipping sack, 10 kilograms. Here the sack is pre-made and filled before the product weight is applied to the seal. So seal strength is at ambient temperature governs, no hot tack. Required seal strength 24 Newton per 25 millimeter. Film yield strength determines the minimum requirement thickness. The most economic option minimize film weight uses 111 microns compared to 160 and 145. Less material, same performance. Case number 4. A snack packaging shipped at 3,000 meters altitude. As the package travels to altitude, the external pressure decreases from sea level atmosphere to 70 kilopascals. The internal gas pushes outward. Using the pressure balance equation, force equal delta P times PD squared divided by 8, the required peel force is 6.8 Newton per 25 millimeter for a 3,000 meter destination. If shipped by aircraft at 4,500 meters, 9.5 Newton per 25 millimeter is needed. The practical lesson: always ask the customer how the product will be transported. Air freight has different requirements than ground. Case 5. Spouted pouch for apple. The spouted corners are the critical weakness. Two flat films meeting at the corner cannot seal uniformly without calculability. The sealant with the lowest viscosity at shear rate of 1 to 2 per second is selected. Even though it has a higher zero shear viscosity, for the 250 milliliter format, 75 microns of sealant is needed instead of 50 because the larger spout diameter creates a larger gap to fill. Case 6. Oxygen barrier for grated Parmesan cheese, 2.3 kilograms. 120-day shelf life, 5 parts per million maximum oxygen intake. Working through the calculation, 5 ppm of the product weight is volume is 8.05 cubic centimeters of the oxygen. Over 125 days, and 0.24 square meter of a package area with 0.21 atmosphere oxygen partial pressure, the required OTR is 1.33 cc per square meter per day per atmosphere. Film at 30 microns meets both mechanical requirement for a hot tack strength and the oxygen barrier requirements. There are other 2 case studies that I leave for the listener to go through the slides, and if you have any question, you can put your question in the comment for that. 7 things I want you to take away from this video directly from the science. 1. Heat sealing is a 5-step molecular process. Step 4, interdiffusion. Builds the bond. Step 5, crystallization. Locks it. If either step is incomplete, the seal is incomplete. Every machine parameter and material property maps to one or more of these steps. 2. Temperature is the dominant variable. It controls melting, diffusion rate, and sealing window. The seal initiation temperature is not an arbitrary spec. It reflects the melting point and molecular architecture of the sealant. 3. Seal strength scales with the square root of dwell time, not linearly. Doubling dwell time gives 41% more strength and costs you production rate. Know the trade-off. 4. Metallocene PLE outperforms conventional LLDP for some reason. That narrow molecular weight distribution always beats broad molecular weight distribution. Uniform surface composition, no low molecular weight surface segregation, predictable diffusion across the interface. 5. Hot tag is always lower than seal strength because crystallization contributes to ambient temperature strength, but not to hot tag. The difference between the two tells you how much the crystallization step is controlling the final bound strength. 6. The sealing window width is the industrial robustness metric. Wide windows, robust process; narrow windows, fragile process that fails when anything changes. Design materials and parameters to maximize window widths. 7. For bioplastics, blending PLA with PBAT, PLA with PCl is currently the most practical path. No single bioplastic sealant offers comparable sealing performance to optimize conventional polyethylene. The blends are the compromise that makes sustainable commercially available. If you have a heat sealing problem in your work or a question about any of the material science or test methods we covered, drop it in the comments. I respond to every question. If this was useful, subscribe. I publish a new video on polymer science and flexible packaging every week. The DSC analysis video is linked in the description. It connects directly to what we covered today. The book this video is based on, Heat Sealing in Packaging by a group of researchers of Professor Ajji, Jalaluddin Safar, and Kanani, is linked in the description if you want to go deeper into any of the topics. It is the first comprehensive reference on heat sealing and I highly recommended it. Thank you for watching. I will see you in the next one.